Oh, yes, yes.
And it is there's a guy I'm not sure you know in this market accounting, the one for get money from this year. You were talking about that.
Yeah, it's great. And yeah, and he could have gotten the room named after himself, I guess, but yeah, he wanted to do it in honor of David. Yeah.
This office available. It's a little bit like forest or something. Wealthy guy. No, the safe, but it's
Hey.
Well, that's the way things are going.
So, welcome everyone to the second day of the workshop. So our first speaker is Remmen. We'll be talking about Stringy dynamics from an Amplitudes Bootstrap. So, Brandt, I'd like to do that.
All right, sounds good. Thanks very much. Well, thanks to the organizers for the invitation to speak here and for what's been a fantastic workshop so far. So today I'm going to be talking about this set of 3 papers focusing mostly on the latest one, where we are trying ambitiously to essentially derive string amplitudes from first principles. And what I mean is we're using the Bootstrap method. So the Bootstrap method is, of course, rightly celebrated as essentially a means of discovering new physics without using high-minded principles of geometry and thought experiments, but instead asking the right math question of the S matrix. And so you can, of course, get essentially for free gauge theory, GR, etc. In this way, But what hasn't been answered is what is the analog for string theory? What is the math question to which string amplitudes are the answer? And of course, we're interested in this because it would be desirable to, in some sense, prove that string theory is unique. And so we should ask ourselves, what is it that string amplitudes do? The slogan is that they unify GR and quantum field theory by taming trans-Planckian singularities of graviton amplitudes. But more pragmatically, string theory accomplishes this by adding an infinite tower of massive higher spin degrees of freedom. Now, of course, in QFT, the thing about a massive higher spin degrees of freedom is you can't add just one. If you add one of them, they generically make your amplitudes worse because of powers of momenta in the propagator numerator. So string theory solves this issue by adding an infinite tower where they kind of telescope and cancel each other's divergences. But an interesting question is whether or not string amplitudes are the only consistent way of adding an infinite tower of massive higher spin degrees of freedom. So in particular, we'll be looking at Veneziano's famous amplitude from 1968 and asking how unique it is. And of course, this being a conference on QCD and the QCD string, this amplitude has its origins in the prehistory of QCD, before David's discovery of asymptotic freedom. And it was, of course, constructed to solve basically a phenomenological puzzle of the late 60s. Perturbative methods seemed at the time potentially impractical, and so there was this S-matrix program of trying to write down an amplitude sort of ab initio that would match the observed Regge trajectories seen in the meson spectra. So here we have an old plot, Chu-Frauchi plot showing mass squared versus angular momentum, and of course everything is lining up on a line. And we understand this now in terms of the QCD string. Another aspect that Veneziano was trying to capture was this sense of dual resonance, the sense that really you should only be adding states in one channel and that they'll magically resum into states in the other channel. So don't add both S and T channel particles, add just one, but an infinite tower so that the propagators will resum into the infinite tower of spins. So what we're essentially asking in this talk is, what is the set of dual resonant functions? Is there life beyond Veneziano? And so what we're going to do is derive 4-point amplitudes. We'll imagine that the external states are just scalars, so I'll strip off the polarization data. And we'll be asking ourselves whether we can get the amplitudes, that is the dynamics, just given some minimal data in the form of the spectrum. So just giving ourselves the m squareds and the angular momenta, along with a few physical constraints. So the physical constraints are crossing, polynomial residues, and high energy boundedness. And we'll indeed find that the distinctive form, the gamma gamma over gamma of string theory, arises very naturally. So we'll understand sort of why that was, in a sense, inevitable. But we'll find some interesting generalizations, in fact, an infinite space of new objects that accomplish many of the same mathematical miracles. And it would be interesting if these new objects have some use either in a formal aspect of string theory or even phenomenologically. So by crossing, I want to think about colored scalars. So these will be color stripped amplitudes. So we just have cyclic invariance. So we just have S and T swap symmetry among the Mandelstams. We can talk about fully Bose-symmetric amplitudes if we want to do this for gravity. That'll probably have to be in the coffee break. I don't think I'll get to gravity in this talk. But you can just think of this as kind of gauge theory amplitudes with the polarizations stripped off. Polynomial residues. So for this requirement, we want the nth exchange state to have spins running from 0 to n, just like string theory. We're just going to put this in by fiat. And what it means is that the residues of the amplitude on the nth exchange state are polynomials in T of degree n. We can think about more general polynomials. In fact, we thought about this in a paper from last October, but I'll leave that aside for this talk because it turns out to be really interesting even in this space of just spin from 0 to n. Non-polynomial residues are also of interest in the context of the EFT hedron, but again, we'll leave that aside for this talk and take kind of a hardline view of locality in the sense of just wanting polynomial residues. Finally, high energy boundedness. So what we want is for the amplitude to vanish in the Regge limit. So fixed T, large S, we want the amplitude to go to 0. That sounds maybe like an intensive requirement, but remember, if you dress this with the f to the 4th polarization data, this is literally just Regge boundedness. It's requiring that the amplitude scale like s to the j at large S. So what this means is that there's no pole at infinity, so we can rewrite the amplitude in terms of its own 0 subtracted dispersion relation. So I can rewrite it in terms of just the imaginary part of the amplitude integrated over the real s-axis. And if I now input one further assumption, which is that I just have a bunch of tree-level exchanges, I get for free dual resonance. So here I have derived dual resonance, not assumed it, just derived it again from assuming crossing symmetry, high energy boundedness, and no pole at infinity, or equivalently well-tamed UV behavior of the amplitude. So it will be this requirement that we want to impose and see what are the allowed polynomials, what are the allowed R sub n's, such that this resums into a dual resonant object. And of course, this is famously one of the hallmarks of string amplitudes that differentiates them from field theory. And it's clear in string theory why you have dual resonance just at the level of a cartoon, in that you can deform an S channel string worldsheet into a T channel one by just sort of squishing it. Right, so now let's input a spectrum and see what we get. So first we're going to, again, inspired by whether you like either inspired by string theory or inspired by the data from the mid-60s, we'll input an integer spectrum, m squared equals n. So now we have a 2-variable complex analysis problem in order to implement crossing symmetry. And to 0th order, nobody really likes multivariable complex analysis. So we'll turn it into a single variable complex analysis problem by going to special kinematics. So we'll fix T to S minus K, where K is just some arbitrary integer, and see what we get. So we'll input this into the crossing equation, and we'll kind of massage the sum a little bit so that we get a finite sum on the right-hand side and an infinite sum that's a difference of 2 residues on the left-hand side. Yeah. Well, okay. So none yet, because I haven't told you what S is, right? All I'm doing is I'm pinning T to S minus K. The reason I'm doing that, though, is because I'm going to be extracting some poles, and I want to relate different poles. So the reason I'm choosing S minus K is because on the nth pole, I want T to be sensitive to a different pole so that I get this sort of recursion relation. If I had chosen a different spectrum, and in fact, later on when we do Q-deformed integers, this will be different. But if I had chosen a different spectrum, I would have wanted to choose T such that I just shift to another pole. It's a pole skipping type of thing. Yeah. Any other questions? Sorry? Yeah. So I'm assuming that that the UV has some small coupling, and so this is effectively just the tree level amplitude, and there will be higher order terms that I'm dropping. Yeah, it's a non-trivial assumption, but it's what's true for the Veneziano amplitude. So we just want to see are there other tree level amplitudes like Veneziano that do all the same things. Good. All right. So we have this constraint, and so now we want to see what it takes to satisfy it. So we notice that there are a finite number of terms on the right-hand side, and that there are no poles at integer s less than or equal to k. So we just want to impose the same thing of the right-hand side. So demanding that gives us this beautiful constraint on the residue polynomials, that the nth residue evaluated at n minus k equals the n minus kth residue evaluated at n for k between 1 and n. So that's really nice, but This is strictly speaking a crossing inspired constraint. It's not strictly speaking necessary nor sufficient. And the reason is easy to see. It's not sufficient because we, again, chose special kinematics. So you could imagine if nature is sort of conspiring against us here, that it could be possible to satisfy crossing on these special kinematics, but not away from it. It's also not a necessary requirement because, again, this representation of the amplitude in terms of an infinite sum, this side converges for t below threshold, for t less than m naught squared, or it also converges in the sense of providing the right residues on all the s channel poles, and vice versa for the crossing symmetric image. Now, when we plug in these special kinematics, this is not at generic t, we're at integer t. So you could worry about convergence. Nonetheless, we will find sort of in post that everything we've done here is justified. We will, in fact, be able to use this constraint to find crossing symmetric amplitudes that are fully convergent and dual resonant. So we'll just take this as given and see what we get. Right, so we have n conditions. If you just do the parameter counting, we have n conditions on the n+1 free parameters in the ansatz. So let me just solve that for you. I'll define lambda m as the lambda m comma m coefficient here. Also, everywhere I'll write factorials extended to complex numbers. So rather than write a bunch of gamma functions, I'll just pretend factorials are functions of complex numbers. And we have the general solution here. So we have still an infinite number of free parameters, one for each index here. And we find numerically that if you choose the lambda m's, this real sequence, such that the S channel representation converges, that always yields a dual resonant crossing symmetric amplitude. So we have already an infinite parameter generalization of Veneziano. Now, most numerical choices you would make for the lambda m's don't converge into anything that you can write down analytically. So let's explore this space a little bit and see if we can write down some beautiful analytic structures. Roughly speaking, lambda m has to fall off as of order 1 over m factorial in order to converge. But such things as a polynomial in m over m factorial also works. Yeah. So in fact, inspired by that, let's just choose the simplest case that converges. Let's pick lambda m equals 1 over m factorial. So then we can use the Vandermonde identity to rewrite this residue very nicely as just t plus n factorial over t factorial n factorial. So that's a very simple polynomial. And so we can rewrite the amplitude. We can plug in this residue. And we can use a few identities. We'll use the definition of the Pochhammer symbol, which is just a ratio of gamma functions. And we'll use the definition of the hypergeometric function. And finally, we'll use an identity called Gauss's summation theorem to find that this is indeed just the Veneziano amplitude. So we've derived the Veneziano amplitude really simply just from a few physical constraints, well-posedness of the amplitude in the UV, crossing, and a very simple choice of the free parameters, and it falls out naturally. So we now understand, in a sense, why the gamma gamma over gamma structure was natural. Now, I said that in order for this to converge, we want lambda m to fall off as roughly 1 over m factorial. So a nice way of parameterizing that would be to shift the factorial in the denominator, or equivalently multiply by some polynomial in m in the numerator and sort of take that as a basis and see what's the more general set of objects. So let's do that. Let's choose a nice basis for a generalization. We'll write lambda m as r factorial over m plus r factorial. Here r is an arbitrary real number. And again, the residue has this nice closed form. And what we're now going to use is the definition of the generalized hypergeometric function, which is, again, just an infinite sum over a bunch of ratios of Pochhammer symbols, to rewrite our amplitude in terms of 3f2. Now, the whole point of this was to build a crossing symmetric amplitude. This doesn't look obviously crossing symmetric. So now we're going to use an identity on the 3f2 due to a 19th century German mathematician named Thome. And we can rewrite this amplitude for this choice of lambda as just Veneziano times this dressing factor, which is manifestly crossing symmetric. So here, again, this is a manifestly crossing symmetric dual resonant amplitude. So in a sense, this object is just as compelling as what Veneziano wrote in 1968. And so we should study this to death and see what its properties are. Yeah. Yes, we are going to check that shortly. In fact, positivity of the partial waves isn't manifest at the level of the Veneziano amplitude. One has to check that it's positive. It was just proven without using no-ghost theorems in string theory, just proven at the level of the amplitude in dimensions up to 6 by Nima and company about a year and a half ago. Yeah, so we're going to check that. So in fact, that's the next thing. So we're going to read off the residues. Eventually we'll be more general, but just as a warm-up, let's do this in 4 dimensions for massless external particles. So we're just going to take these residue polynomials, write them as sums of Legendres in terms of the scattering angle, and demand that all the A coefficients are positive. Because what those are effectively the squares of the couplings between 2 of the light states and 1 exchanged state. So let's do this. You can compute the partial wave coefficients explicitly in terms of sums. Now, these aren't manifestly positive. They're alternating sums, just like for Veneziano. And these here, S1 is a Stirling number. So here's what we get. We find, indeed, for R, this is covered up for some reason. For R equals 0, this is just Veneziano, and everything's positive, as we expect. But for other values of R, so here's R equals 1, R equals 2, R equals 3, it remains positive. So indeed, partial wave unitarity is satisfied, at least for some range of R's. And we'll explore that more generally later. But just as a sanity check, indeed, this has a shot at being a real physical theory. Oh, R is this is the 1 parameter extension. So this is a 1 parameter generalization of Veneziano. When R equals 0, this 3f2 becomes 1, and it reduces to Veneziano. R need not be an integer. This has a particularly simple form when R is an integer because of hypergeometric identities. But yeah. It can a priori be positive or negative. Okay, as a spoiler, it turns out there is a lower bound on R that depends on dimension, so it can't be too negative. But positive R is always fine. Good. Okay. No. This is numerical evidence. Yeah. We can analytically understand some of these bounds by reading off, looking at the partial waves for the leading Reggie trajectory or the first or second subleading one. But those are necessary conditions. To understand why it's sufficient just requires checking a large number of partial waves. What does this mean physically? We don't know for sure, but I will show you a very suggestive idea in terms of what it could mean. Yeah. So okay, in the high energy fixed angle limit, we should also ask whether this amplitude is well behaved in the UV, whether it falls off nicely. String amplitudes, of course, are famously well behaved in the UV. So for high energy fixed angle scattering, we get the following scaling. We get this e to the b factor, where this b is the same object that shows up for Veneziano, plus some term that goes like a power law. So in the physical region, one has negative b, and so the amplitude falls off as a power law, r over st. Except in the R equals 0 case, where you get the famous exponential fall off of strings. So it doesn't fall off exponentially like Veneziano, but it behaves more like a field theory in that it has power law decay. In the unphysical region, where t is positive, b is positive, and so the high energy scaling of the amplitude is just dominated by this e to the b factor, which was in fact proven that there had to be this sort of asymptotic uniqueness of Veneziano, proven by Karen Huo, Komargatsky, Sever, and Zhiboydev in 2016. So this agrees with their uniqueness result. What about the Reggie limit? So high S fixed T. We know that this will be fine because we actually input it at the very beginning of the talk by construction, but let's just check. Indeed, we get S to the T dominating for positive T. For negative T, we get, again, power law behavior. So this has the expected Reggie scaling. Now, to get back to Tony's question, it looks like there might be a worldsheet interpretation of this amplitude. So remarkably, our 3F2 hypergeometric amplitude can be rewritten in terms of an integral representation as a double integral in terms of two dummy parameters, x and y. And this reminded us of the Kobe-Nielsen form for the 4-point Veneziano amplitude, which is, of course, a single integral. And in fact, if you look at the 5-point Kobe-Nielsen string amplitude, so 5-point Veneziano, and then fix special kinematics, so pin some of the Sij's to just fixed numbers, -1, -r, -1, you get back precisely our 3F2 amplitude. So it's as though our hypergeometric amplitude might be obtained from taking the 5-point string and doing something to it. What that something corresponds to, we don't know. We just know that formally it corresponds to fixing some of the Sij's. So that's the best interpretation we have right now of the underlying physical degrees of freedom, but it's a very interesting open question. Right, so time's getting on. So now I want to jump to another choice of spectrum. So we've looked at the integers. I now want to look at the Q-deformed integers. And the reason is because historically, of course, string amplitudes predate the realization that the theory was about strings, and so it's worthwhile exploring new amplitudes that can lead to new physics. And this was done in 1969, 1 year after Veneziano, by Daryl Kuhn, and then tragically forgotten for decades. This is the Inspire graph, and you can see it's just a flat line pretty much until the last year or so, when there's been a surge of interest. And what he did is he essentially Q-deformed the Veneziano amplitude. In mathematics, there's this whole field of Q-deforming everything in sight, and it starts with Q-deforming the integers. So let's assume our m squareds are the Q-deformed integers. So the nth Q-deformed integer is just 1 plus n squared all the way up to, 1 plus q squared all the way up to q to the n minus 1. So when q goes to 1, you just reduce to n. And for q less than 1, you have some accumulation point in the spectrum. So starting from that point and defining some new kinematic variables, sigma and tau, we can write down a dual resonant ansatz that's essentially a Q deformation of what we wrote before. And we can go to special kinematics. So now, rather than t equals s minus k, we'll choose tau equals sigma minus k, so the suitable Q-deformed version, so that t shifts to the shifted pole. And again, imposing crossing and running through the whole exercise that we did before, we have some general solution for the residues. So now we still have additional freedom. We can dress each term in the sum with a prefactor that goes to 1 on the pole. And doing that won't change any of the residues. So we're going to do that with benefit of hindsight. So we'll choose to dress each term with a factor of q to the tau times sigma minus n. And doing that and choosing a simple Q-deformed version of 1 over m factorial for the free constants yields a dual resonant crossing symmetric amplitude whose S-channel sum converges. And it's precisely the Kuhn amplitude. And you can see it's just the Q deformation of Veneziano dressed with some branch cut factors. Good, so we understand where the Kuhn amplitude comes from. And I'll just plot for you the Chu-Frauchi plot for people who haven't seen this. So the Kuhn amplitude has these accumulation points depending on the value of Q. Sometimes it's referred to as a logarithmic deformation of the Reggie trajectory. All right, so we now understand where that comes from, sort of building it from the ground up. And I should add, this is not how Kuhn derived his amplitude. He derived it on purely aesthetic grounds. He wanted to write down an amplitude that had some infinite product representation. But instead, we've seen it's just something that naturally falls out if you want any dual resonant amplitude that has the Q-deformed integers as its spectrum. All right, at high energies, the Kuhn amplitude has this funny double log that I've also found amplitudes that have that double log in some recent work with Juan Maldacena, we built some string theory constructions where you have open strings attached to D branes and ADS that have exactly this double log. So this is physically healthy. And the branch cuts that appear in the Kuhn amplitude suggest a sort of ionization process. Recent work by Christian Ipsen, who's here, has shown an apparent breakdown of unitarity in the Kuhn amplitude exponentially near the branch point, even though the partial waves on all the poles are unitary. So that could possibly be cured by choosing a different prefactor. That's an open question that people are working on. I just mean that you have, all right, so you have some poles that march toward an accumulation point, and then above that point, you have logs, you have branch cuts, which suggest, some multi-particle state. Yeah, exactly. It's not known whether it's truly a continuum because there's not a fundamental description of what's going on. Yeah, it's purely suggestive. Yeah, that's right. So in fact, right. So let me go back. The residues here are just polynomials in T. The ansatz is indeed a purely tree level ansatz. So where on earth did the branch cuts come from? The branch cuts came, remember, sigma and tau have log S and log T in them. So the branch cuts came from this dressing factor, this q to the tau, q to the sigma tau dressing factor that I added. Now I added that by hand because you can just verify that if you don't add this factor, which goes to 1 on all the poles, if you don't add it, this amplitude doesn't converge. This infinite sum just blows up. And but this same dressing factor occurred in Kuhn's construction, which involved an infinite product. And there, the reason for existence of this factor was to turn a polynomial in 1 over T into a polynomial in T by having a q to the log S log T factor. So, this is one example of a dressing factor, but I can in principle add any contact terms I like. And, this is something that Christian has been exploring. Yeah, that's right. That's right. Yeah. Right. So the reason I'm doing this is because we're trying to make contact with the Kuhn amplitude. So we started out by asking, is there a way of building a tree level amplitude with Q deformed integers and that's dual resonant? The answer is no, unless you add these dressing factors. And the cost of adding them is introducing logs. And that seems sort of inevitable. It might not be so strange physically because, like I said, you can kind of wave your hands about ionization processes, but no one really knows. Yeah, they start at the accumulation point and go off. Yeah. That's exactly what we found. Yeah. But again, I stress the constructions that Juan and I looked at, they captured various constructions involving D branes and ADS captured various aspects of the Kuhn amplitude. There was no single construction that completely got at the Kuhn amplitude, but it's conceivable that some slightly more complicated version will. Right. So now what I want to do is ask whether the Kuhn amplitude can itself be generalized, and can I connect this back with the hypergeometric amplitudes at the beginning of the talk. So we'll consider a slightly more general choice for the lambda m's. Again, it's something that sort of falls off like 1 over m factorial, suitably Q deformed. And we can run through the same sort of exercise and use what's called a Q-Tomei-Kummer-Whipple transformation. And we have a new class of crossing symmetric dual resonant amplitudes. So this is a Q hypergeometric amplitude. The 3 phi 2 is the Q hypergeometric function. And you can see it's the Kuhn amplitude dressed with some kinematics. Yep. No, this is just a number, right? So the dressing factor occurs here. I'm assuming here the same dressing factor as for Kuhn. So this is the dressing factor. This contains the branch cuts. But I could write down anything here that goes to 1 on the pole, and it would be safe. This is, in a sense, the simplest thing that does the job. No, that is done with benefit of hindsight. So, all right. So the lambda m's that we chose to get the Kuhn amplitude were the following. These turn into just 1 over m factorial when q goes to 1. But this q to the stuff was chosen so that we get these nice q gamma functions. And then adding the shift here was done so that we get this nice q hypergeometric function. In principle, yes, you could play around with all sorts of alternative choices for the lambda m's. This was the only one that we found that's particularly nice. Yeah, exactly. Good. So I want to stress this object unifies everything I've written down in the whole rest of the talk. So this q hypergeometric amplitude fills out this whole green plane. Oh, there should be an r there. So right. So q equals 1, arbitrary r, are the hypergeometric amplitudes we looked at previously. R equals 0, arbitrary q, is the Kuhn amplitude. The Veneziano amplitude sits at this point, and we've now filled out the whole space. So we can indeed look at partial wave unitarity. Here, I won't look at unitarity on the branch cuts because that's an open problem. But just looking at partial wave unitarity here, we can now generalize what I wrote down earlier and even shift the spectrum with an arbitrary m0 squared, so an arbitrary starting point for the tower. And we see some special points. So here, everything in teal is okay from the point of view of unitarity. And each line here is a particular dimension. So this is 4 dimensions, 5 dimensions, 10 dimensions, and 26 dimensions. So here, for 26 dimensions, the bosonic string sits at this corner of the allowed unitary parameter space. In 10 dimensions, the superstring sits here at this red dot. And in 5 dimensions, there's this interesting point with non-zero r. So this is a hypergeometric amplitude with exactly critical dimension 5 and r equals -0.5. And that's an interesting theory. It's compelling from the point of view of unitarity. So we'd like to understand that special case in more detail. Here, if I fix m0 squared to 0 and I float q, we again have different regions where this is unitary. In dark teal, it's unitary in all dimensions. And above this line, it's unitary in 4, 5, 10, and 26 dimensions, respectively. So I could put those together and show you a full 3-dimensional plot. So here we have 4, 10, and 26 dimensions. And this wedge extrudes to arbitrarily large r, it appears. Arbitrarily large r is okay. We haven't looked at that yet. So in principle, Jepsen's interesting paper on the Kuhn amplitude should be generalized to the branch points. Computing and checking partial wave unitarity on the branch cut is technically harder than just doing it on the poles, and so that's something that that should be done. It hasn't been done yet. Well, yeah. So I'll leave discussion of this for Christian's talk, but essentially he took t derivatives in the forward limit, and to rule out q near 1, he had to take higher and higher t derivatives. So to explore the full space of q from 0 to 1 would require actually a lot of computation. But I want to also stress, though, remember we also have these hypergeometric amplitudes in the q goes to 1 case, where we understand unitarity more completely there, where there are no branch points and it's just a bunch of poles. All right, so just to recap, I mentioned, but I should mention it here, that we have some physical interpretation, perhaps, of the Kuhn amplitude in the sense that we found some string backgrounds that capture various aspects of Kuhn. So that is, if you take an open string, fix it to a d-brane at fixed bulk depth in ADS, and if you spin it, you get an accumulation point in angular momentum, just like the Kuhn amplitude has. But it approaches the accumulation point as a power law, not exponentially, so it's not quite Kuhn. If you stretch it, it approaches the accumulation point exponentially, but not in terms of spin, just in terms of this semi-classical quantum number n. Finally, if you take 2 of these strings and you collide them and scatter them, then at very high energies, you indeed get the double log structure that the Kuhn amplitude has. So it's conceivable that some combination of all three of those processes would exactly get the Kuhn amplitude, but that's an open question. But what's interesting is, we wouldn't have looked at this if not for the Kuhn amplitude. So these bootstrap constructions can point the way toward the exploration of new structures within string theory itself. And just to remind you what we've done, we've derived this new infinite parameter family of amplitudes that are Lorentz invariant, crossing symmetric, have polynomial residues, and remarkably satisfy UV boundedness, and they're dual resonant, just like string theory. And for particular choices, we get these beautiful hypergeometric structures. Everything in sight Q deforms very nicely, and it appears to be unitary. And so it appears to satisfy, it satisfies partial wave unitarity. Yeah. Yes. Yeah. Numerical exploration indicates consistency with partial wave unitarity. Right. So right now we're looking at all sorts of other interesting directions. We're pursuing the dual resonance bootstrap for amplitudes with different mass spectra. I can tell you right now, we actually found a way to build endpoint amplitudes, so arbitrary endpoint that have a world sheet representation with arbitrary spectrum for the first n masses, and then that asymptotes to Reggie. That we end up using some Galois theory. I can tell you more about it in the coffee break, but as an example, we can write down string-like amplitudes at endpoints that have a KK spectrum at low energies and that asymptote to Reggie. So these are very exciting. They look totally different than everything I've written down here, but yeah, ask me about that offline. But again, we're interested in figuring out what's the underlying physical system giving rise to all these new amplitudes. And hopefully, eventually, we would like to prove that either all these new objects might be somehow secretly sick, or maybe they turn out to exist in string theory itself and illuminate some corner of the theory we haven't explored. Ultimately, this is essentially the only path to proving uniqueness of string theory. So it's a worthy goal, I think. So thank you. Yeah. Yeah. Well, so we've thought about doing that. Okay, I mean, part of the problem is we're getting a lot of mileage out of the assumption of UV boundedness, right? That's what allows us to assume to get dual resonance. We could, in principle, drop the UV boundedness assumption, but then we might have to put in more by hand in order to have a tractable problem. So we might have to drop UV boundedness, but put in dual resonance as an assumption. And then maybe there's more that you could do. Yeah, that's an option. Yep.
Really interesting. I'm wondering about trying to think back on the history. I wasn't there at the time to physics, but I have the impression that we practice on some level different modes, string modes, but then there was a problem when you do loop, love-based from the physical dimension.
Right.
Here, you're far from that state.
Yeah. I mean, to do loops, it would be desirable to have an understanding of the fundamental degrees of freedom. For what we're doing with our new project, loops might be possible because, again, we have world sheet representations of the amplitude at endpoint, which would be something necessary in order to do loops. So we might be able to do loops with this new stuff. But the other comment I would have is that, indeed, while the critical dimension, while you see it at loop level, in string theory, somehow the tree level amplitudes also kind of know about the critical dimension, in the sense that you can also read off the critical dimension as the maximal dimension where partial wave unitarity is satisfied. So you can read off d equals 10 and d equals 26 purely from unitarity at tree level. So we're hopeful that ports over to any of these new models. But yeah. No, so Let me see. Yeah, so it goes like, s to the t, the Reggie behavior, but then there's plus 1 over something that looks like order s times t. So there are power law corrections for non-zero r. No, there'll be 1 over s squared, etc. Yeah, we just dropped all those. Yeah.
Hi, nice to see you. Yeah. Yeah. So, okay, very good. So,
well, I would say look at the subset now. There's a number of right. Oh, and then what this means,
this does not correspond to like taking say E5. Yeah, we don't have a after oh yeah. Yeah. Well, there. Okay, so yeah, so we try these amplitudes by turning because that was neither necessary nor sufficient, just cause and inspire. There are other solutions. In fact, Tiziano has this interesting paper where he looked at send it out and that. This is something that is not happening. Because precisely it gets high. Yeah. If we relax that, well, I hope that all the things that invade our strange or weird islands like this, it's kind of strange. Yes. So
and then this critical dimension in thought, that's critical in the terms of conflict.
Right. But there are no branch types for that yet.
Yeah.
So you like partially unitary is unitary. Right. Well, yeah. I think it might be some effective theory. Yeah. But I mean, you can see the critical dimension that goes on in the brain, even without the gravitational knowledge. You can see it at the level of the Lorentziano membrane. Plug in m naught squared equals -1 and read off the partial waves in twice 6 dimensions.
You get critical behaviors. You go at 27 dimensions there. Right. So we see the critical partial waves, but yeah, we don't know. Right. Exactly. Yeah. But that requires yeah.
And then seems like it seems like you know exactly. Like, are they not just a particular limit of point amplitudes that satisfy
Well, the 4-point amplitudes indeed are, but if they are coming from one theory, there should be some 5-point analog on this that maybe I get. So if you don't split and
we're asking. Yeah, I don't like maybe cynical question. Like, is it seems like as you said in the beginning, you're asking about So like, what is there is there a reason to think that these objects make sense as a 4-point amplitude and not just because they are just a particular limit of that also satisfies all
well, I think so, because they satisfy a lot of other things. Like, if they were just some weird limit of a 5-point, you wouldn't necessarily or you wouldn't necessarily expect you know, power law sauce,
you saw this coming miles away.
The fact that you get all of that, so it's by basically all the same thing. That's the other bit. Besides the kind of the formal limit of the 5-point, I can give you some underlying Hamiltonian.
No, of course.
But we would be great. That's true. Yeah. But for so far the new stuff that we're doing, it's weird. Version of these. I can tell you if you're interested.
I don't want to like. I can't do this because I'm the question. I don't know if people want to show them. No.
So maybe something like n squared over n plus one. So you can move it. I have a function of s. Like resolve it quadratically, resolve there. And if I take the gamma now I mean, and if I replace s is equal to plus of s. Also, I now I sum over the whole gamma. So I have 4 terms. S with
It's a similar thing, right? Just like
the terms I will have now. Has exactly this structure. And no branch type, because even though F involves the F, but now, so okay, so great. Now I have some but now I can resolve the results of the and there's an actual way to find it. Everything you want. Then you can check. But this now obviously generalizes to if I want to fix the first say 20 times squared. It's not a lot of solving for the roots.
in a poll where one of their arguments. So this is, I mean, we can mount these functions by Bootstrap. But yeah, the insight is.
So how does this thing?
They're part of critical dimensions I wrote down before, and that they are
So yeah,
so they go to S to some power.
So do I understand that? That's incorrect, that basically if you try to draw register interface for say this F.
That's kind of fun, because you were talking about the same too as well.
But then here there are this,
You presented, but some of the same word.
No, the three except I wrote down have exactly the same.
no, but by register
You've done some work
interface,
since.
but
That means that you made it believe it was exactly 1/3. That was You've just been telling everyone it's fractional.
Yeah.
And then it's like there's something that's still linear.
I'm still not convinced.
Yeah.
But then there are
think
terms
it's
that
that
there's
way.
power.
It's like maybe change that.
Minus
1/4 is fractional, so that means it must be adding questions up.
And it's separate.
Oh, I
know.
see. That's it.
That's all we want to do.
Yeah, yeah.
So that is kind of.
Well, we've always.
Here, okay.
Like it's.
It's well, but the power thing.
Yeah, for negative.
Yeah.
Oh, you have like 1.3, I forget what it is, right? Like some other so you just normalize divide by this. This is normal. Well, I'm thinking this number that we put in the sign,
right?
And
Yeah,
it's not one. Yeah, exactly.
Now it's
Now
not
thinking
very.
that's one time.
I love the pictures.
Yeah, okay, so I think, all right. So in a sense, you're worried about spurious poles, right? And
Yeah, basically, yeah.
yeah, so okay, so right, so in the Reggie limit, I said something like, right, this goes like, so the subleading term is 1 over R over 1 plus T S plus some dominant. So you might see you're able, what about spurious pole? And then here's there's the S to the but okay. A way of understanding this is that so the 3F.
This is another pole.
Yeah, right, exactly. So T is -1 is
This is here.
well, it looks like a pole here, but it's not actually a pole in the pole amplitude. The subleading term is higher because if you take I didn't write this in the talk, but if you take R to R, let's say big R equals 1, right? The 3F2 amplitude simplifies a lot. What it ends up looking like is gamma of minus S minus R and then gamma minus E minus R plus though, but this looks bad a priori, right? Because it involves poles, there shouldn't be poles, right? But then it's plus some polynomial in ST over and the spurious poles here precisely cancel the spurious poles.
You say that is probably what happened in this.
Yeah.
These guys versus.
Yeah.
You shifted the linear and added some horizontal ones.
Yeah.
In a way that the spurious singularity is the physical.
But then you should forget the regime all go away. Yeah.
And then, okay, so now you do this quadratic things.
Yeah.
Then what is the picture? Did you try to draw this picture? That's what I started asking about this thing. Do you know for fixed negative T?
Right.
So as to infinity.
So we have a couple ways of doing the quadratic. And what I've written down is one way. There's two ways of doing it, but one of the instructions we have. In the Reggie limit, the amplitude doesn't go to 0 goes to a constant. So what you end up in the dual resonant picture is that the amplitude is some constant plus the sum over it, which is it's like there's fundamental 5-4 term. What's interesting is you can absorb it beautifully if you allow S dependence.
in the RNs. It actually is very nice in that sense. But what that means is, in mentioning them in the example I wrote down, yeah, the dominant thing is just this contact.
Okay. Then what is the subdivision?
I don't think I've computed that yet. But wait a minute. Yeah, okay. So what this looks like in general is S to the F plus or minus the T times the functions.
So there is some analytics in spin.
Yeah,
T does become the
yeah.
but then f of t, so f of t has a branch cut,
Right.
because the branch cut is a function of n, hence because the branch cut is a function of t.
Yeah.
So
Oh, but these branch cuts go away. So what I mean here is S to the F plus times gamma minus F plus S to the F minus times gamma minus F minus. Yeah, so yeah, so what I mean is the branch cuts go away. That's
they go away because just this term and this.
Well,
this
right, yeah, I mean, you can compute this constantly across the branch cut, but I mean, since every square root that shows up with a plus here shows up precisely with a minus here.
And you're roughly plotting this for everything.
I don't know off the top of my head. But what I mean.
This thing does not depend on S, right?
No, this doesn't depend on it. Yeah, so the discontinuities are only.
Yes, then I want,
And this is negative for P below threshold, so it falls off. In the same way that you expect, it's just with a different scaling. It's not
just solution of this equation.
Yeah. So it's so F of T. That's roughly like it's proportional to something like E to the power minus some linear function.
Today or tomorrow, whatever.
Yeah. Okay, so it's large absolute value of T.
Yes, linear.
It's linear. It's here that I'm basically I was wondering if this maybe something like this that's sort of produces some level crossing different here. We have trajectories across, and then maybe you get something like this.
Yeah, I think it has because they're by construction there are no spurious poles. We define the amplitude. We can define the amplitude as a dual resonance zone. So I mean I've defined it in terms of Valenciano, but I can write it purely as a convergent dual resonance zone, where the poles are only at.
But sorry, do you have? I guess what I'm looking for is some mixture of your two things, because this has pure this thing exponentially decays apart negative.
Yeah,
right. So it doesn't have this yet.
Yeah.
Do you have something where you have basically non-zero R? Can you mix the two?
We haven't done that, but indeed, so we could take our hypergeometric amplitudes and
I wonder if it will produce something like this. Like it's important for something that I'm thinking about whether take that one. There is no whether this level crossing happens or whether it's avoided level crossing.
I see.
Because there are some. I mean, I don't know. I'm oscillating between what happens in electricity. Like if you go to electricity literature, it seems like there are like two schools of thought.
Okay.
That formulated in the relation between like soft and hard formula. And I think translating in the level of this picture is that some people think that this happens, like avoided level crossing, or some people think that actually level crossing happens.
Okay.
And this trajectory is not continuous.
I see.
So I think there is, and I myself oscillate between the two.
Okay.
And so I wonder if there are examples. So I think you sort of provided an example where the level crossing happens, and also if you like this paper by Bolchinski, or like the famous paper with quadratic, they basically have a very similar picture. Like, remember picture from the paper, right? It's like horizontal one. I mean, they have been going at all angles.
Right.
So that it would be nice to see like there are examples of both and
No, that's interesting. No, there's no reason why. Wi-Fi.
And so it will probably have this more parallel, but we expect in CD behavior, have this monoidal structures, like a chance of something. Okay, thanks.
Okay.
So you import this condition.
Oh, no. I'm saying that, consider some theories. Some information.
So crossing symmetry is
What you wrote, I think,
we've imposed crossing symmetry, and then our onset is
straight.
It's not strictly necessary nor sufficient for crossing.
Okay.
All we're
there's a transition, very powerful changes with this parallel linear concept, parallel changes with the parallel linear dimensions. But there is no
right.
Now we can say, okay, let's say so right form with
forwards,
right? And two things can happen. Explain. One thing that can happen is that avoid
this is like
I would expect naively avoided to expect that once we can break
some discrete lattice.
Then avoided double crossing happens, and this
and it turns out it's nice.
This crossing
this is
here
to get crossing at arbitrary.
Well,
right. I mean, we're
but there's
all
some
just in the sense that we want Rn avoiding polynomial country, and we could in principle have allowed it to be some arbitrary.
That is what happens.
You
probably know the picture that is for the people doing the delta J plot. The range of trajectories and then this different range of trajectories. Here we have C, J. They have
we could in principle have asked for
J
a different polynomial, and then we just out
J. I know you probably saw this picture. It's basically you if you do it for screen deals, you get free theory.
Generic lambda summed up but
single trace whatever.
if you take generic lambda, you don't have crossing, right? So you could imagine taking generic lambda and imposing crossing at a bunch of random points in S and T space rather than at the integers.
Right, so they
that would in principle constrain lambda, but I don't know. I mean, in general, it wouldn't be close.
Now, when they do then the picture is informed the level that gets avoided, and then you get this curve, and another one. It keeps going until levels. All levels get. If we keep the quantum numbers for that. X, the archive number, that levels do not, even though it's an integrable system.
I should. I know of one that is not captured by our. So I know
there is maybe some prevalence of this point of view.
It's a sense of
and this basically some people hold high.
We wrote down. Let's say I take alpha prime and send it to alpha prime over K.
And then they have discussions. Foolish have like
so then
same nature.
So let me call
the amplitude. And I interpret it the following. They say the same nature means some continuous you can kind of get one and there is some
over these Ks.
So that's what I kind of thought.
And this is also healthy.
But now I think that maybe
and so
it has of course it's infinite. Of course, if you find at the end,
does it have USB-C?
No, it's not HDMI.
But now I
No, we have a USB-C, and I guess this should be better. I mean, what is this?
Kind of HDMI is not exactly straight.
Yeah, this is the one.
And they end the leading trajectory where the global lie.
because.
also goes through and pierces it,
well,
and they actually
some of the
cross.
sums that we wrote down,
Even though they have the same
occur
quantum
like
numbers.
this.
That large M, there is some maybe indication that they can cross. So that's why.
Oh,
Which is
sure, I'm
kind
sorry,
of
I'll
okay.
no, don't worry, it's fine.
You take here the cross again, you get the picture like.
Also, if I
Oh,
remember correctly.
That's what I'm saying.
Were post.
Well, I mean, these guys become very.
Oh, yeah, yeah, right.
Okay, I don't, this green curve, I don't, not saying that it's green curve has- Let's not try to, so let's say that it's around here, the trajectories that we care about.
Yeah, right, indeed, yeah.
So-
those, the variable that's appearing in the denominator in the sum.
So let's say this is the leading trajectory,
As
we both play,
that's
okay,
negative.
and this is the leading BFL trajectory.
That is
That's
one.
weak coupling, it's like J equals one, okay?
So yeah,
So now, of course, this curve is not exactly straight, it kind of starts to bend
So
up,
the hypergeometric amplitudes.
and that curve in reality is not exactly straight, kind of
then I don't
of
see
bend in this
how
direction.
this
Or
construction
whatever.
goes wrong, because
You know, in
seems
this
to
direction,
me,
it starts to
if you
bend
sum
some
over
way.
poles,
And then the
Yeah.
question is, do they get
the domain of
connected,
convergence is.
or do they
exactly the
kind of
same.
go through each other?
That's
Some fashion.
right, but,
And then, okay, the other. Let's say.
That's right,
pair,
but,
the leading one here.
but-
the leading-
the sum that we wrote down.
Okay,
involved
this-
R n minus K.
Yeah,
Yeah.
Imagine there was some quantum number. That
So in this sum we got
the
by.
black guy had a different.
by
causing.
causing
This because by
And
crossing
they
you
cross.
Yeah. Yeah, that's
This
right,
may
that's
be
right.
very, very.
Um, So yeah,
Yeah,
this
and
means
this may be
we
very, very.
formally put it outside of the domain. So that's why crossing inspired.
Yeah.
But it turns out to be enough to get,
Oh, it-
but it's very almost everything in the sense that.
But this, well, but this, the idea of this crossing.
But yeah, there's some more general way to do this, that doesn't involve giving T
And
as my.
this DFL limit. So there are, this trajectory is generated by different number of Wilson lines, and that they do not need to pass that. Basically, I have like cables on lines, does not need. There is some, the DFL from is one in the upper triangular form. In the basis of the Wilson line. Which is funny because it's not like some ordinary. And
long
can
past.
still discuss what it means from a similar point of view, but that would suggest this picture of them. Maybe you cannot mix
No.
like number
I
of
would.
questions, you cannot exactly label of that is not very difficult.
Yeah.
Some physical symmetry, right? So.
Right. And it depends, I mean, sometimes it's about.
No, but clearly we know that that's what we see.
Oh, yeah.
Well, we're assuming Quark scalar is in a planar diagram, so we're if we grant them color scale about the like allowing yeah and yeah, I think it's poker and yeah, it ends up being right. It's right. No, it's good. That's very good.
Okay, welcome back. To the second session of today's workshop. So our next speaker is Alessandro Nada, and he will be talking about numerical calculation of the color flux to thickness using continuous normalizing flows. And I think it will be a good opportunity to see how machine learning techniques can be applied to this kind of investigation. So please, Alessandro.
Thanks, Andreas.
Like 15 minutes, plus 5 minutes.
Thanks, Andreas, for the introduction. So this is a work made in collaboration with people in Torino, in particular Elia Cellini, who is a PhD student in our group. So essentially, I have two goals for this talk. The first one is trying to understand, trying to explain why it makes sense to do a numerical calculation of the flux tube thickness starting from the Nambu-Goto string. And the second one is to understand why we're using this continuous normalizing flow, which is a deep learning architecture, in order to do so, and why it would be better, for example, than a Markov chain Monte Carlo. Okay. So let's start from, just a bit of background on FX theory. So we know that this is a very important non-perturbable framework that in principle provides an effective description of the confining flux tube in Yang-Mills theory. And in particular, if you look at some observer like the polycular correlator or a Wilson loop, we know that this is described in the EST framework by the partition function, okay, Z. And well, this is physically interesting, phenomenologically interesting, maybe even because we can extract directly interquark potential from this. Okay. Now there is also another observable, which is quite important, especially in discriminating which kind of string will eventually be the right one, if you want, which is the flux tube thickness. Okay. And this, from the Nambu-Goto side, I mean, from the effective string side, it's not so easy to compute analytically. Okay. So this is the first reason why we would like to compute numerically, not so much Z, which we know analytically pretty well, but this W squared. Okay. Now the idea is that okay, you want to do it numerically, that's fine. Why don't you use an MCMC? So a Markov chain Monte Carlo, for example, an HMC. The idea is that it's not very good at this job. The non-locality, kind of non-locality of the FSD string action, like the Nambu-Goto action, is not very well suited for an HMC, or well, maybe an HMC could work. Indeed, maybe at the end I will show you how it works with respect to our deep learning architecture. On top of that, calculating the partition function in a Markov chain Monte Carlo is doable, but it requires quite a lot of work. And on the other hand, this kind of architecture called normalizing flows are very well suited for this job, and I will try to explain why in the second part of this talk. Okay. So this is what we are going to simulate. Essentially, we are essentially discretizing the Nambu-Goto string. This is the action that I will be using. We are literally putting our field variables on a square lattice. We are putting periodic boundary conditions in time and the in space. And I'm mentioning also that this is a kind of expansion. This is a trivial expansion, if you want, which gives a free boson as the first term, because it is relevant in computing the partition function itself. So we know very well the analytical solution of partition function. The point is that it's not so useful in this case because we are doing it on a lattice and it's a box. So we need a finite size solution. And this is known only for these two terms of the action. And this is not super important, but because we are not really interested in partition function, since we already know it. But we are going to use it as a benchmark somehow, as a way to know that we are doing that our numerical calculation will be eventually correct. Okay. Yeah.
I mean, this is a 3D theory, right? So,
yeah.
So it has the while and all of the.
Yeah, but it should be. It should go away in the large.
Oh, the large.
Yeah. Okay, so second observable, which is interesting, which is more interesting if you want, is the thickness of the string. And the way that we compute it numerically, this is like a snapshot of our lattice. The green points are the, if you want, the quark and anti-quark. So where we put these boundary conditions. The active points are the blue ones, and the red points are also active. So we are updating those points. And this is where you actually compute the observables, the phi squared. If you would like to do it, for example, in Yang-Mills, you would do something similar. You would have a Polyakov loop, another Polyakov loop, and then you will look at the essentially a wall sheet defined by this, and then you dislocate another operator, so it's a 3-point function. You put a plaquette somehow at a certain distance with respect to this plane. Okay, so this is kind of the same kind of operator. Okay, indeed. We know the analytical solution for the thickness in the case of the free boson, and in particular in the two regimes, the low temperature and high temperature regime. Low temperature, well, the inverse of the temporal direction, temporal size is what you would call the temperature. So this is why we're calling this low and high temperature. L is the time direction, the size in the time direction. So these are the two behaviors that we are also going to check at the end of the, when we are going to look at the numerical results. And if you want to look at an example for a gauge theory, this is a relatively simple gauge theory. It's maybe the easiest DZ2 gauge theory. This is more or less what we expect in the high temperature regime. So you see that this should be linear in R, and this is what is proved numerically on the side, of course, of the gauge theory. Now we would like to do the same, but on the side of the Nambu-Goto string. This is the critical radius. It depends essentially on the string tension. Okay. Okay, so a bit of deep learning. So normalizing flows. I'm just using this because it's nice. So the idea is that you start for something which is trivial. So maybe this is just a Gaussian distribution. So something that you can manage, that you understand very, very well. And maybe you want to describe a distribution which is less trivial. Okay. Now let's look at some formulas first. This is pretty recent and also has been applied in lattice field theory in the last few years. I will comment on that later. So it's a class of deep learning algorithms. And the idea is that this normalizing flow is nothing but this invertible indifferentiable function that essentially takes a prior distribution, which can be, for example, a Gaussian distribution, a trivial, or even a uniform distribution, something that you can completely control, and somehow manages to generate a new distribution called Q theta. This theta represents all the parameters of this normalizing flow. This could be millions in principle. This is where the magic on neural networks happens, which is as close as possible to our target distribution. Target distribution is, of course, our Boltzmann distribution, ideally the one of the thing. And the interesting thing, the very powerful thing, is that for normalizing flows, you're able to write explicitly this generated distribution Q of theta. Okay, it depends on the prior and the Jacobian on this transformation. What we are going to use in the end, it's the output of this transformation. Okay, this is the final configuration phi, if you want. This should follow this distribution, and if you're lucky, if you're good enough, this Q of theta will be close enough, similar enough to the target distribution that we can actually use it in a meaningful way. Okay. Okay. Yeah, kind of. So the advantage is, in principle, if you think, for example, about lattice field theory, is that this is a tool to defeat critical slowing down, in principle. Because if the configuration, the number you extract from the prior distribution are all uncorrelated one from another, also the final ones will be. And so if you're able to build such a flow, in principle, you're defeating critical slowing down. And this is somewhat similar also for Nambu-Goto. Maybe I will comment on that later. Of course, you needed to train this. So what's the meaning of training? The training is essentially taking some quantity. In this case, it is this Kullback-Leibler divergence, which is a number somehow, which tells you how similar two distributions are. In this case, the one we are generating and then our target. And if you manage to minimize this and bring it as close as possible to zero, then you'll probably be lucky enough that you are able to use it properly. Now, of course, the configuration that you generate with this generated distribution, this latent distribution, more properly said, are not exactly following the target distribution. So you have to correct from that. And the one way to do so is using this reweighting-like procedure, which I'm looking at here, showing you here. This O in our case will be our flux tube thickness, not to be confused with this W tilde, which is the weight. And I'm mentioning the weight because this is also very powerful, and this is also an important pro with respect to an MCMC, is that you can compute the free energy, well, the partition function directly. This is very, very powerful. You could do it in principle with an MCMC, but you need to do some cooking. Okay, and in this case, it's a directed computation. This is very nice. Okay. I'm not going to comment on everything I said. I wrote here, just to say that in the last, I would say, 4 years, in the lattice field theory community, there has been a strong push to understand how to use this. There have been using several architectures applied more or less always on toy models or very, very small volumes somehow. But there is a lot of going on, and I think this is a very nice and pretty much alive part of the lattice community. The only architecture I will be mentioning today is this continuous normalizing flows, also quite recent, which we have been using. Let me just comment that one final comment is that there are several open issues in this field, more or less, mostly are concerned with how the length of the training actually scales with the volume or with the dimensions. Okay, so this is definitely non-trivial. Okay, cool. So a few words about the actual architecture we're using. These are continuous normalizing flows. The actual flow is essentially the solution of an ordinary differential equation, which is parameterized by something which is in principle arbitrarily complicated, which is this neural network v of theta. The way that you are going to actually use it in the end is that you're putting your random number generator, whatever you use to generate the prior distribution that you're using, and then well, the parameters of your neural networks, you're just inputting this to your solver for this ordinary differential equation, and you're getting the output. Okay. Okay, you're also going to need this, but I don't have time to comment on that. Let's take a bit of a closer look, just to give you an idea what v theta is. So v theta is this guy here. This k of t is a kernel with some Fourier coefficients, and this w, this capital W, is actually in this case it's a perceptron. It's the actual neural networks inside. Okay, so you can see where the actual neural networks are in this architecture. The idea is that again, you would train this, you would train again with a Kullback-Leibler divergence. You will need some time, perhaps hours, perhaps days. This depends how complicated your target distribution is. But if you're lucky enough, you're getting to you're managing to generate a distribution which is very, very close to your target distribution. A way to understand that is to use a metric, and in particular, this effective sample size. This is a number. If this number is 0, you're out of luck, in the sense that your training didn't work. But if it is 1, it's a perfect training. So Q of theta will be exactly P. Of course, this never happens, but so you want to be as close as possible to 1. But also numbers which are around 0.2, 0.2, 0.1, 0.2 could already be used. Okay. Okay, good. Let's look at some numerical results from Lambugoto. And then let's take a look immediately at this ESS, okay, at this number. This essentially tells us if our trainings are working, if our architecture is meaningful, and the answer is yes. You can see here several values. We are in the high temporal regime here, so R is much larger than the temporal size. What's happening here? Well, the ESS is okay. Several values of sigma. These are all quite large. Just to give you an idea, I mean, in young Mills, sigma is 0 point something, but we are working on that. Of course, this decreases when a sigma decreases as well. And also, this is also quite easily understood. If you increase the volume, well, a probability distribution of the same theory with a larger volume is more difficult to describe. Same thing happens in the low temporal regime. A bit lower, the ESS is a bit lower, so this is a bit more complicated to simulate, but still okay. Okay, and we're also working on better architectures so that even smaller values of sigma can be simulated properly. Okay, just a couple of slides, which I'm not sure if I have enough time to actually comment. Okay, very good. So I will just rush through it. I said that before that the partition function was useful to understand whether we're doing things correctly, and this is more or less what's happening in this slide here and here. Since I have just a couple of minutes, I will just skip both and focus on the thickness. Okay. This is what we were looking. I mean, what we wanted to look at, and this is a plot for sigma equals 100. But we actually did this global fit of this rather complicated function for the thickness. These are several coefficients, most of which have some expected values. And then from the global fit, this global fit actually was quite a success for us, because all the values of this global fit are in perfect agreement with the numbers just below. And if you just pick one value of sigma, you can plot this on R with several values of L. And this is exactly the same behavior that we were looking at before, looking at this simple gauge theory. Okay, so the linear behavior, this guy here in R is satisfied, and exactly with the coefficient we were looking for. Okay, you can do a similar thing also in the low temperature regime. This is a different global fit with a different functional form. Same thing happens for these several of these coefficients, and we were, I would say, quite happy in seeing this, that you can actually find a perfect agreement with what we are expecting from both the low temperature and the high temperature regime. So I think out of time. This was, in my opinion, non-trivial. The idea that we can sample efficiently the probability distribution of the Nambu-Goto action. Of course, we need more work to understand what's the best architecture to do so. We found excellent agreement both for the partition function and the thickness, and this essentially tells us that maybe we can trust these are kind of architectures to do numerical simulations of the Nambu-Goto string. And if we trust this, then we have a tool that we can use in any regime. Okay, not just low temperature or high temperature. We can literally do it at any lattice for any size. Okay, if we're able to train it, of course. And on top of that, we can also add terms and go perhaps beyond the Nambu-Goto and see what happens. Okay, I think that's it. Thank you for your attention. Yeah, sure, of course. But of course, you always look at the regime in which the effective string theory is valid. So usually you don't go too close. I mean, for example, in an interquark distance, you cannot go too close. At some point, this breaks down. Yeah, that will break down, and you're not allowed to use. Yeah, you're not allowed to use it anymore. Of course, yes.
But nothing stops you.
No, of course not. Yeah, sure. In principle, yes. But you cannot connect anymore with the Yankees.
Looks like your model is
yeah, so there's most. For the low temperature, I'm not completely sure why it works worse than well, it might depend actually just from the fact that I think here just the volumes are just larger. Okay, and well, lower string tension means we are essentially getting closer and closer to a critical point, and this becomes more and more complicated for the neural networks to understand what is going on. Essentially, yeah, if you want the correlation length are getting bigger and bigger, and so the neural networks has to understand how to connect points which are further away in space. And yeah, but they're also very difficult for a Monte Carlo, right? So in a Monte Carlo, you see this from the point of view of integrated autocorrelation time. The autocorrelation times explode, right? On the side of a normalizing flow, you would see that the training times explode. Now the question is, and this is a kind of an open question, which explodes faster somehow.
Yes.
Our next speaker is who's going to talk about the theory of the
Okay, so thanks a lot for putting together this beautiful workshop. So today I'm going to be talking about some work in progress. So in fact, I have not much to say, but with Sergei Dubovsky, Guzman Leadership Plus, Ashamoni, and Sherzad Saleh, Sergei is in the audience. It's about an old question, but that we still believe there are some things that we need to understand about it. So, okay. But okay, this is the plan of the talk. Most of the talk will actually be about the point 2. Okay, so the reason why many people are here today is that it's by now pretty clear that QCD, or more precisely Yang-Mills theory in the planar limit, admits in some sense a dual weakly coupled description in terms of a string theory. And we would really like to understand this string theory and use this string theory for the real world. So what does this mean in practice? It means that there are 2 scales in planar Yang-Mills. One is a scale set by the mass of the first glue ball, roughly. And the other one is a scale which is nc times that. And there is a 2-dimensional string theoretical description which we believe should hold up to the scale lambda nc. Now, how do we describe this string theory? Of course, we don't know, but at least in this regime here, we have a very viable tool, which was already described by Alessandro, which is EST, effective string theory. And here there is a long history. I just got these 2 papers, which are maybe the state-of-the-art modern understanding. This EST is very powerful and gives us glimpse also about the description in this regime here, through the approximate integrability of the worksheet, as it was pointed out in this beautiful work of 2014. And yeah, this came a bit as a surprise, but we now believe that's a strong hint. Okay, so mostly to set up notation, but also to review something, since this will be useful for later, let me describe what is effective string theory. So the setup where effective string theory was the most studied is that of a string wrapping a cycle of a torus and moving in a time direction. So the description holds as long as you take the cycle length to be much larger than the string length, which is roughly the inverse mass of the glue ball. So, and as you all know, effective string theory is actually a theory of Nambu-Goldstone bosons. It just describes the symmetry breaking pattern of Poincare dimensional group to the 2-dimensional Poincare group times transverse rotation. And this is described embedding the coordinates of the string in this way, in the torus, with xi being the d-2 Nambu-Goldstone bosons. And then you have an action that at leading order coincides with a Nambu-Goto action just out of geometry. And then you have a derivative expansion as long as you consider small excitations corresponding with respect to the string length. The first non-trivial term in this action comes in this form is the extrinsic curvature term, which is roughly some covariant derivative of the worksheet coordinates. And this is the induced metric. Now, this setup is very well understood, as I said before. The question is what does this setup teach us about the mass spectrum of Yang-Mills theory? And again, also this is an old question. In fact, maybe it's the original motivation of QCD in the first place, or the string theory description of QCD. And the idea is that mesons or glue balls are described by open or closed, respectively, rotating strings. And to a somewhat non-historical path, I believe the first evidence, well, a very concrete evidence for this came through our modern understanding that effective string theory, if you take this, that action I showed before, you just compute the quantum numbers, not the masses of the corresponding glue balls or mesons, in fact, glue balls in 3D Yang-Mills, you match very well the quantum numbers on the lattice. So this is strong evidence that this old idea is actually correct. But in fact, the oldest evidence, which is what we want to improve upon, is that there is some predictive power. And the predictive power, I said effective string theory holds when the string is long, but as I think you all know, relativistic kinematics implies that a rotating string becomes long when the angular momentum becomes large. And if you extrapolate the prediction that you get just by taking Nambu-Goto action rotating to the real world spectrum, if I get the famous, I think, Strauchy plot or Regge plot, I don't know, where you see that the meson lie on a straight path mass square versus angular momentum. So let me just review a bit more this. The setup is the following. For a meson, you expect 2 quark and anti-quark at the endpoints. For a global, you expect the string to be cusped at 2 points. The length is roughly 1 over the angular velocity, and the angular momentum is roughly 1 over the angular velocity square in units of the string length. So you see that when the length is large, the angular momentum is large, or vice versa, and therefore you should have effective field theory. Now, there is a problem with this effective field theory, or there is something we don't fully understand yet, which is when the length is large, it's true that you have a long string, so you should have effective field theory, but you have endpoints which move very fast, close to the speed of light, essentially because the velocity is omega f. And in the case of the global, they're actually cusps. And this cusp leads to an apparent breakdown of the derivative expansion. And as I will review in a moment, this is essentially because this is a singularity from the viewpoint of the worksheet metric. And the question is, how do we describe this setup within effective field theory? Okay, so the problem is there both for open and closed string, but for open string, it's somewhat simpler because we avoid the problem of the singularity at the cusps. So I'll describe that. Okay, so let's look at this problem in the face. So how do you describe a rotating string? So we want to have a semi-classical description. So I'll just take a classical solution of the Nambu-Goto action. And you can write it like this. So I'm writing Nambu-Goto action. We'll have the x0 coordinate, we consider with the time coordinates, and it will be rotating this x1, x2 plane. And you can add extra coordinates if you are in dimension larger than 3. And the worksheet metric will read like this. There is a free parameter alpha f, which is determined by the boundary condition. So the point is that, as you see, if alpha f is 1 or close to 1, you see that this metric has a singularity famously. And in fact, if you take just pure Nambu-Goto action with Neumann boundary condition, which would be your first guess for an open string description with light quarks at the end, you find that alpha f equal 1. You recover at leading order the Regge trajectory, but you see that here there is a metric singularity at the endpoints. And if you remember, you have a derivative expansion to curvature invariance, so metric singularity is a problem. Okay, so let's look at this problem a bit more closely. So let's try to add perturbation on top of our Nambu-Goto action. So as I told you before, perturbation are written in terms of this extrinsic curvature object. You can just plug the classical action as a guess and see what happens. And you see, okay, these perturbations are naively suppressed by powers of the angular velocity. Angular velocity was like 1 over square root of j. So they seem small, but they're not integrable. There is a singularity here. The same problem shows up if you compute energies or daughter Regge trajectories. Okay, you might say, that's my bad. I'm not allowed to just plug this in here. I'm not allowed to assume massless endpoints. There is Young-Mills, there is strong dynamics. I should write a mass term at the endpoint, which might be generated somehow. But the strong dynamics, and write the mass to be roughly of the only scale I have, the global mass. And this indeed cures the singularity. It puts this alpha f not to be 1, but 1 minus something which is proportional to omega. But this doesn't cure the effective field theory problem. Again, because now all these higher derivative terms, which should be suppressed with respect to one another, so larger n should be smaller in effective field theory, they all contribute at the same order. In particular, if you compute the contribution to the leading Regge trajectory, they all contribute j to the 1/4 plus corrections. Maybe even more dramatically, I wrote this term here, which is the word line of the endpoints, but the acceleration at the endpoints is huge. They are spinning close to the speed of light on a circle. So acceleration is comparable to the word line. So there is an issue with the derivative expansion. And the same issue complicates every calculation you want to do. So the goal of my talk is not going into the detail of how you solve this issue, but I just want to give you the physical picture of how you, yes? I don't think for in effective string theory you have the Polchinski-Strominger term, which becomes singular at the endpoints. And no, I think that actually the first paper actually tackling this issue is this one by Remmen and Swanson. We use polyacroft formalism, so I'm going to review. And you also there have an issue. Of course, you don't have this issue in fundamental string theory because you can quantize the theory exactly, and there is no Polchinski-Strominger term. But as soon as you put that into by hand, which you need to in away from 26 dimension, you see the issue again. Yes, thanks. Okay, so the physical idea of the solution of this problem, I think the first paper dealing with it was Remmen and Swanson, but I think we extend it in Nambugoto language and to dotted radio trajectory, is to think that in effective field theory, you don't resolve the endpoints. This is pretty natural. Rather, these endpoints are embedded with some effective thickness that parameterizes your ignorance about them. Now, what does this mean? This means that you have a new cutoff of the endpoints. But once you have a cutoff at the endpoints, it means that you have renormalization of the boundary action at the endpoints. So you will have a boundary action, and this boundary action will get renormalized by the bulk operators below. So those all contributions which I saw before, they were not really bulk contribution, they're just normalization of the boundary action. That's a bit unusual because it happens at a classical level or a quantum level, but it's the same usual story. The maybe most non-trivial part about this story is that actually you might want to naturally identify the cutoff here with the only length scale that you have in the theory, which is again the string length. But however, the metric at the bulk and the metric at the endpoints receive a huge redshift factor, if you remember what I showed before. So if you want the proper time close to here, it's very different than proper time close to here in terms of the worldsheet metric. It's not even in terms of worldsheet metric, just because it's spinning very fast. So it's a usual GR factor. And this factor turns out to be square root of omega. So it depends on the angular momentum. So this means that if you write your battery action, it's a derivative expansion, derivatives times the string length. But now you rewrite this proper time derivatives in terms of time derivative of the bulk, which is what measures your energy. You will have a factor of 1 over omega to the n. So in other words, it means that having a local cutoff here, which is what you want, what comes naturally out of any effective field theory construction, which is the string length, will result in effective cutoff on your energies or excitation on top of the radio trajectory you can deal with, which is suppressed by a factor of omega or by a factor of square root of j. In practice, I guess I understand this is not obvious from a single slide, but this means that the expansion here in the calculation we'll do effective field theory will not be in 1 over j, it will be in 1 over square root of j due to this redshift factor. Okay. So sorry, I don't know what happened. Okay. So once you get this physics at end, I think it's pretty simple to construct the action. I will not detail here power counting of the boundary action, what happens. I think this will be a bit too technical for a 15-minute talk. But let me just give you a glimpse of the result. The boundary action looks something like this. It's a bit odd because it's written in terms of the acceleration of the endpoint boundary. So you have two copies of this, one for each endpoint, rather than the world line velocity. But it's still, you should remember, this thing is spinning very fast. So the acceleration is non-singular at the endpoint. So you can make sense of this. And you have to make use of several field definitions actually to see that this action is complete. But eventually, the main point is that you have only two coefficients at the first leading and the first subleading order. So this is all your ignorance up to order j to the -1/4. And maybe the only other technical thing that I want you to appreciate or to believe me is that this action is fully reparameterization invariant. So your only technical constraint is reparameterization invariance in the tau coordinate. So the rules are clear, and this is a sample calculation you can do. Now you can compute the radio trajectory, which is and the dotted radio trajectory most importantly, and predict correlation between the coefficients here and the coefficients here. So the leading term is well known. The subleading term, I guess it's also well known, even though maybe not understood in this perspective, and there is an extra subleading term. This M and M2 are trivially related to those coefficients there. And omega here is the angular velocity, it goes to the corner square root of j. You see that here you predict this correlation with this subleading term in the dotted radio trajectory. So this is the excitation energy on top of this radio trajectory. Here this is the angular fluctuations. So this is exists in any D, and this only exists in D equal to 4 or larger are the transfer fluctuation. For n equal 1, these predictions are trivial, because they just correspond to changing the angular momentum of the leading one. So that's why they go like omega n. And we also have the subleading prediction here. I'm just not showing for the sake of economy of slides. So the main point, actually, you see this correction goes like omega to the 3 half. The next one will be like omega to the 5 half. So the predict, or you see it here, the expansion is 1 over square root of j, which means that your derivative expansion breaks down a bit earlier than you would have guessed naively. So you actually have to take n much smaller j to the 1/4. Naively you would have guessed n much smaller than j to the square root of j. And n is an integer. Now, the non-trivial check that you can do is now this calculation was done with this boundary action and Bugoto, but now you can include back higher derivative bar terms, like extrinsic curvature. And now you can check what happens to this prediction. They stay the same after normalization of this coefficient m and m2. So this boundary action actually realizes the progress at the beginning. All these things that we couldn't compute now just we normalize our ignorance in the boundary action. So it's a standard effective field theory. Okay, so in the last 2 minutes or 1 minute, I just want to tell you what we plan to do next. Okay, so this story for the open string maybe was theoretically interesting, but our main motivation is going to work closed strings. And this is because there is a possibility to make contact with data. Now, there is an extra technical complication in this case. If you have closed string, is that now the action at the two cusps that you now want to think again as some effective field theory blobs will be constrained by full diffeomorphism, not only diffeomorphism in tau. So you have a two-dimensional diffeomorphism. And this creates some complication. There is also a physics question. You know, this cusp, you might want to think of it as a closed string, full-fledged, or you might want to imagine that there is some degree of freedom here. It could be some gluon physically. Like in some spirit, you can imagine maybe some spin 1 degree of freedom at the cusp. So, and this is actually a physics question that you need to, the only way to address it is to compare with data by making prediction. Now, how do you compare with data? Well, the story of the effective string taught us that it's a non-trivial question because the derivative expansion beyond the leading radial trajectory doesn't converge as well. But a lot of progress was achieved using this approximate integrability to resum a number of corrections. So there is also a theoretical question here. Does this rotating string setup or the open rotating string preserve in some sense this approximate integrability? And can we use it to make precise prediction for lattice data, for instance, in these papers? So I hope to report about this in the future. And with this, I thank you.
We'll have like 3 minutes for questions.
The best literature on bench rotating strings and ATS
Mm-hmm.
right there. I guess there everything is well defined.
But I think it's an equal Fourier and Fourier miss a lot of that, right?
Yeah, yeah. But you can compare, for example,
Right. So no, that's a good question. So like this rotating string effective field theory there, you should predict the anomalous dimension of this operator phi, many covariant derivatives phi. And presumably this 1 over j correction will turn into log of j corrections, some of which have been computed by the Bootstrap. So it would be nice to match it. We didn't do, but I think it should be possible. Yeah, so if you know the string, of course you can. But I mean, this operator, this gauge theory operator, somehow exists also in more general theories. So I would say, like, I'm just saying where this could be useful is in a Bootstrap perspective.
For example, suppose there's other.
Yeah. And there is some Bootstrap idea about what this operator, how to make this calculation for this operator. It's like Caronuot and Yesebisi have some paper about it. This could provide a physical interpretation of the result. Professor Srimoyee, I think, has something about it. So I think that would be useful. I think in any for you know the string, so now maybe it should apply in some regime, but maybe it's less useful.
Do you have a oscillating string would be like big and then it becomes small that again
If I understood, I didn't think about it. So fine. So you want an oscillating string which becomes small. I mean, it depends how fast it shrinks, I guess. Yeah, I don't know. It's possible that some of this technology can be used there. I don't have an answer for that. Yeah.
Yeah. Yes.
Our next speaker is Srimoyee Sen from Iowa State University. First confinement.
Can you all hear me? Or? Yeah, I guess. Okay. So thanks very much for organizing this workshop and inviting me to give a talk here. So as you can see, two of my collaborators are in the audience, Alexi and Theo, and then Larry Yaffe is also a collaborator on this work. So this is something I've been working on over the past probably now 4 years. So we have some new results, which is in preparation, and you hopefully see in a few months. So with that, let me get into the talk. So I'm talking about gauge theories here, the ones that exhibit both confinement and Higgs regimes. So, so let me quickly tell you what I mean by confinement here. So if you took the gauge sector of the theory and removed any mass that you had in the original theory, the theory should still exhibit confinement. That is, all the gauge fields are gapped. So that's what I mean by confinement. And what I mean by Higgs vaguely is that if you add the matter sector back and then somehow are able to condense the matter sector, it will give mass to the gauge fields, and that's what I mean by Higgs. So this is sort of the sort of hand wavy picture of what I'm talking about, and then I'm trying to make it more concrete. That's what the aim of the talk is. I suppose yes, that's what I would say. Yes, yeah. These are, I'm going to stick to, yeah. Okay, so there's a standard lore in the community inspired by Fradkin and Schenker. So the standard lore is the following. It says that, let's say you have a gauge theory that exhibits confinement. So let's say your matter sector, so your matter sector is in the fundamental representation of the gauge group. You could take scalars. And let's say you are dialing a parameter in the theory. For example, the mass squared parameter of the fundamental fields. And so you go to a regime where you have kind of confinement, to another regime where you have Higgsing. And if there is no global symmetry, which changes realization as you go from confinement to Higgs, then there's no way to tell these two apart. Okay, that's the standard law, and that's inspired by Fredkin and Schenker's work in 1970s. So what I'm going to do in this talk is that I'm going to tell you that the results of Fredkin and Schenker hold in the class of theories that they work this out. But there is another class of theories where you would be inclined to apply the same intuition that you would be deriving from Fredkin and Schenker, but those don't apply. So that's what I'm trying to get to here. So here, I'm showing you 2+1 QED. And so here, the example that I'm showing you, there is a phase transition in this model. So you have a gauge field sector. This is a abelian gauge field. This is charge 1 matter field. It has a mass squared parameter and a quartic interaction term. So here, if you dial the mass squared parameter, if the mass squared is sufficiently negative, then phi condenses. So you are in the Higgs phase, and the photon is gapped, right? And then if mass squared is very positive, then these fields are heavy and you have an ungapped photon. So clearly there is a phase transition between the Higgs and the non-Higgs side. And this is, of course, expected because there is a symmetry that changes realization as you go from one to the other. It's the U1 topological symmetry. So that is spontaneously broken in the mass squared positive side, and it's not broken in the negative side. So there's a phase transition here, but there is no confinement in the mass squared positive side. This theory is, or what I mean is that there's no linear confinement in this theory, right? So now, so the point is that Fredkin-Schenker doesn't apply in an obvious way to this example because there's a symmetry that changes realization as you go from one regime to the other. But now let's introduce confinement here by putting in monopoles in this theory. And when you do that, the photon becomes gapped and you get linear confinement. And then there is no symmetry that changes realization as you go from one side to the other. And so Fredkin and Schenker applies here, and there is actually no phase transition separating the two regions. So this is an example, which is a concrete example of Fredkin and Schenker. But now I want you to do the following. I want you to tweak the original theory slightly. So what I want you to do is to add a spontaneously broken global symmetry to both sides, the so-called Higgs and the so-called confining side. Again, there is no reason to expect a phase transition from symmetry principles because you're adding this sector to both sides, okay? And then I'm going to tell you that there's going to be a way to tell the two apart when you do this. Now, before I go there, let me quickly tell you why I'm considering this such a strange model. It's because of QCD. So it turns out that QCD at finite density exhibits something like this. So in QCD at finite density, baryon number symmetry gets spontaneously broken, and you have a superfluid phonon at finite density. So that's why I'm doing this. So this is how to tweak the theory. So you have this standard gauge field, U1 gauge field. This big D is 2+1, so this is three dimensions. I have two charged fields. One of them has charge +1, other has -1. MC squared is the mass parameter for these two fields. Here, I have implemented a symmetry between the plus and the minus field, so that's why they have the common mass squared term. Similarly, there's a common quartic term as well. And then on top of this, I'm going to add a neutral scalar field to this problem. So that's phi naught. There's a corresponding mass squared parameter. I will dial this mass squared parameter in such a way that this phi naught gets condensed. So this is going to give me my spontaneously broken global symmetry. Now, on top of that, what I'm going to do is to couple the charge fields to this phi naught field. Okay, so this is what this is telling you is the global symmetry in question is such that phi plus and phi minus have charge 1 and phi naught has charge -2 under this global symmetry transformation. So you can keep phi naught condensed and then dial the charge mass squared to go from a region where these two are condensed to a region where they are not condensed. So that would be going from Higgs to confinement. Okay. Okay, so now in this case, you can consider vortices in the phi naught field, right? So you get superfluid vortices. So now what happens on the Higgs side? So on the Higgs side, phi plus and phi minus have vacuum expectation values. And if you have a vortex in the phi naught field, this cubic term tries to create a vortex in this combination field, phi plus and phi minus, okay? And so now on the Higgs side, that means that either the plus field or the minus field will have a vortex. So then phi naught vortex becomes a flux tube, right? So this is a gauge vortex. So now let's say you want to compute a Wilson loop around this phi naught vortex. And if you do that, it gives you a phase of pi. So it's stuck at -1. What happens on the confining side? On the confining side, naively, what you can think is that plus and the minus fields are heavy, so you can sort of integrate them out. So you just have a vortex in the phi naught field. Now, if you compute the Wilson loop around this vortex, you're supposed to get a phase of 0. Okay, so these are not flux tubes anymore. So if you looked in more detail, you would see that there's confinement and string breaking. That's really what is going to give you a phase of 0. So, so you can see now that there is a way to tell the two apart, the Higgs and the confining sides apart. Question is there a phase boundary? So clearly we have a sharp distinction between Higgs and confinement. Now, before I end the talk, I want to give you a little more details on this, how to get to this Wilson loop being 1. So in principle, in the continuum, it's very hard to do a calculation, but you could formulate this theory on the lattice and try to do a strong coupling calculation on the confining side. So this is something we do, and the paper is not out. We're hoping that it'll be out in a few months. So we do this in the Villain formulation. Here I'm showing you the neutral field sector. So this kappa is the VEV, corresponds to the vacuum expectation of the phi naught field. And so this is the neutral sector. And then I have the gauge sector here, and these are the charge field sectors. And you go to a regime where this coupling is strong, and you can then compute the Wilson loop, and you can explicitly show that in the strong coupling limit, there's no phase on the confining side, and there's a phase in the Higgs side as you go to the other limit. So with that, I'd like to end. So here's the conclusion. We have shown that there's a sharp distinction between Higgs and confinement regimes of this type of gauge theory, where you have this spontaneously broken global symmetry on both sides. This is relevant for dense QCD. What next? Well, we want to locate where exactly this transition is. So we did a calculation, a strong coupling calculation, which is valid in very strong coupling limit. And then we have the Higgs side, but we want to locate exactly where this transition is. And so we will have to simulate this on a lattice and see where that transition is. And then we want to understand what's the order of this transition. And there are many other questions to think about. So with that, I'd like to end. Thanks.
So let's go to questions. We have
does not seem like a problem. The position on the board, there are conditions where you have the main wall, disturbance from the main wall. That wouldn't expect anything in the bulk to have all low energy occupation. But when you put the vortex, you could also consider the example of gray. Is you want to reduce the growth in 36 and stuff. And then you would have the main wall, and this would be a transition on the junction of the domain. Not in the top. Why do you think it's the transition of the top?
The example that you're connecting to, I don't think directly relates to what I am talking about. So the domain wall example, the two sides of the domain wall are actually in different phases, right? They're not.
No.
So that's a different example, I think.
So what I would think, the example I'm thinking about is, let's say you have massive quarks of young mills that they go high. There's a spontaneous breaking of mass one flavor, and then you dial the mass of the quarks all the way to zero. There's no phase transition at all. You know, when you have very light one quark, there's no Wilson movements or anything, period gap in the bulk all throughout. But on the domain wall, Srimoyee and Cyber on this paper showed that there's a transition on the domain. You can study in the large end, at least there's a almost massless and there's a transition on the domain wall.
So you're saying that the two sides of the domain wall are in the same phase?
Yeah. So, but you can have a transition on the domain wall. On the domain wall, there's a TQFT with.
No, because you are going from one phase to another phase, and there's a transition on the wall. That is, it's a function of space, right? There is a transition. So the two regions are not in the same phase. But I don't think that's relevant for what we're doing here anyway. No, the two sides, you have two bulks, right? You have one bulk on one side of the domain wall and another bulk on the other side of the domain wall. Those two are not the same phases, right?
You can show that there's some non-local world, let's say, tractable. There could be two interpretations. So one possibility might be true. There's only a bulk. It could also be found there's something happening in the fall. And you can only tell that it's it'd be not shocking after all. Exactly how you see it. A priori, like you have to.
Okay, I'll make a prediction. You will not find any phase transition.
Well, we have already figured that in some order in a condition.
Yes.
Does happen in a regime where people are under control that the actual fall phase position precisely position in the order.
But is it a phase transition?
Yeah, it's a first order phase. That's right.
Yeah. And the question is that a phase boundary, then everywhere in the phase diagram. But that, I agree a priori, right?
I think you should take Gabriel.
Yeah.
Well, it's more of a comment. First of all, I completely agree with you with the transition between the Higgs and confinement phase. And I completely agree that there's some degree with spontaneous result. Where I disagree is that, first of all, I think we probably disagree on what the symmetry is. And I think the order parameter is a non-local one. And you can often have transitions, not thermodynamic transitions, involve non-local order parameters. In this case, I think singular transition type of order parameter. Second thing I think is that the physical distinction between phase and Higgs confinement has to do with the physical distinction between confinement type. On general grounds, the spectrum of the theory is always going to be gauge variant and polar equal, in fact, nevertheless, there is a distinction between confinement. There's a type of confinement in the confinement phase, which involves essentially, well, I would have to define it, but it has to do with the formation of trajectories, the formation of fluxes, even if they break. You can describe this thing in a definite way. That's distinct from what happens in the Higgs phase. So there's a physical distinction between the two phases. And there's also a symmetry distinction between the two phases. And it can be shown that if the transition between the different confinement types coincides
Right.
with the distinction between the transition between the types of symmetries. It's not a thermodynamic transition.
Well, so the limit where we calculated, there is a limit in 2+1D where you can show that there is a transition. So it's possible to do it in 2+1D because you can write sextic terms in the phi field, in the scalar fields. So there you can show that when you dial the charge masses, you have a first order transition, as Alexei was pointing out, and it is a thermodynamic transition there.
In general, even in frequency, in say lattice field in Higgs field, there's you can go continuously with the confinement phase to the Higgs phase without a transition. So there is actually a transition.
Okay, so that's a little bit different from what I'm showing here, because what we have seen so far is that if you add this global symmetry to the theory, then the arguments of Fradkin and Schenker actually don't apply. So the continuity argument that you would have thought that would smoothly connect the two regions, that doesn't apply here. Okay, so there's no reason to expect in this case that the two regions would be smoothly connected. Okay. Okay.
Maybe about blades. If you put like a syntonic monopole in this case, stuff, I think that there could be a change in the situation because of maybe the global symmetry will be not supported. So you see that it could be different dynamics. I guess when this type of instantaneous transition is included, like you see, like very on charge non-conservation and it's related to this case. In this case, like blame and possible, right? So how this your approach, would react to this additional part?
Oh, yeah. Yeah, I think he wants to add the monopole corresponding to the U1 symmetry of the phi naught field, which
then we can break the global symmetry. Right?
Yeah, we don't want to do that, right?
Yeah, you could just remove the global symmetry in the first place. So that
right, but because the kind of stability adding up this type of transition.
But imagine there is a theory like this. Could argue it's not obvious. But suppose that there is. Certainly, if you destroy symmetry of the model,
yeah,
that's fine. But it would be natural to first get as much symmetry as you can, and only then. That seems like extra, like it's making it more complicated.
No. But if you cannot state this without like by informal use, it's if you're seeing your construction is not quite resolved, breaking this point from inside.
So I think we should.
Yeah.
Again.
All right.
Our next speaker is Bastian Brandt. He talked about high precision spectrum of the Stringy flux tube and effective string description. So Bastian, the floor is yours.
Yeah, thanks a lot. And let me also take the opportunity for thanking the organizers for inviting me and giving this talk here. So I will be talking about a side project of mine since a few years by now, basically since my diploma, which is about the extraction of the spectrum of the QCD flux tube from lattice QCD with high precision, and then basically comparing to the predictions of the effective string theory and try to get something out from that. So I would like to first introduce the topic a bit. Well, I don't think I have to do much. We've heard a lot of talks about this already, so I will be extremely brief here. Then I will show a few results of myself in 3 dimensions, speak a bit about the prospects to do the same things in 4 dimensions, even though that's extremely hard. What has been found in 4 dimensions, however, are massive modes. So I will just show that very briefly on the world sheet, and I will also say a few words whether they might or might not be present in 3D as well. All right, so the basis of all this is, of course, the flux tube picture for confinement. We've heard talks about that already, so I will just consider static quarks for now. I will just neglect string breaking, so basically be working in pure Yang-Mills theory here. And in this case, if we now just start to pull the quarks apart, then the excitation spectrum will basically be dominated by these stringy type of excitations. And we can take as degrees of freedom the transverse oscillation modes of the string here, write down the low energy effective theory for these transverse oscillation modes, which then takes the form of an effective string theory. We can write down the associated effective action, and then all of the prefactors of all of the terms in this effective action will basically be constrained by the residual worldsheet Poincaré and rotational symmetry. Doing all this, we can then compute the associated open string energy levels, and the result can be written down like this. So at leading order, we have this full Nambu-Goto or light cone spectrum here, where we have one non-universal parameter, that's the string tension sigma here. Then on top of that, we have corrections to this. And the first correction originates from a boundary term in the action. It's a 1/R⁴ term with a non-universal boundary coefficient in front. And then we have an additional 1/R⁵ correction, which has a universal coefficient in front up to the string tension here. And then we will have higher order corrections. They start here at order 1/R⁶ if the next boundary coefficient is non-zero, and otherwise with order 1/R⁷. Actually, in 3 dimensions that I will mostly be considering, this term here is absent, so this is not there. Okay, so why am I interested in that? Well, apart from all the phenomenological aspects of this, I also became interested because, well, I thought it is also a good idea or a good opportunity to make contact to holographic duals for large N Yang-Mills theories. And in this picture, the confining string or the flux tube is nothing else than a 4D projection of the associated 10D superstring. So if we have suitable string backgrounds, and I'm absolutely not an expert for this, then one can compute the effective string theory action. And this has, for instance, been shown in these papers here. And then one sees that the non-universal parameters of the effective string theory are related to the bulk properties of the associated 10D string theory. So that means if we can compute these parameters, for instance, from the lattice, then this can provide constraints on possible holographic backgrounds for this duality. And I thought that would be a good way of making contact here. Okay, so what we want to do now is we want to extract the flux tube spectrum from lattice QCD. And I think I don't have to tell a lot about the methodology of the lattice. Also there we had talks about that already. So what we want to do is we want to, well, basically look at static quarks and forget about string breaking. So we are really looking at pure Yang-Mills theory. So then this fermion determinant that you typically had in QCD is absent. Now what we need to do is we need to write down suitable observables for static quark to, well, basically compute the spectrum of a static quark anti-quark pair. And one particular type of observables that we can use are Wilson loops, which are basically just these large rectangular loops on the lattice where one direction is the temporal direction, the other is the spatial direction. Actually, these observables are just very good observables to extract the excited states. because we can actually put non-trivial operators on these spatial parts of the Wilson loop here, which basically just project onto given quantum number channels. So these Wilson loops are very ideal operators to extract the excited state. If one is interested in the ground state, then it's more advantageous to look at Polyakov loop correlators. So what is a Polyakov loop? A Polyakov loop is just a loop of flux winding once around the lattice in the temporal direction. And if we look at the correlators of those, then they are very good operators to directly look at the ground state. Okay, so if we want to extract the spectrum really with high accuracy, then we need extremely high precision. Okay, so that means just what we need to do is we need to use highly sophisticated algorithms. So we need to implement error reduction algorithms and use optimized operators and so on. And in this way, then we can really get the spectrum with a high accuracy. I don't want to go into the details, just telling that this is a highly non-trivial task, and then directly show you some results of what I got. So what I then set out to do was I was studying Yang-Mills theory in 3 dimensions for different values of the number of colors. So basically going from 2 to 6 with the idea of eventually going to the large N limit. And well, what I did was compute basically the static quark anti-quark potential for different values of R. Then I fitted these results to the effective string theory prediction and extracted these non-universal parameters. And what I'm showing you here are the results for this non-universal boundary coefficient for different values of the lattice spacings and different values of N. Okay, so eventually, of course, we are interested in continuum results. So what we need to do is we need to do a continuum extrapolation, and the results are shown here. And now versus 1 over n squared. And now what we still need to do is this large N extrapolation, but this can be done. And this gives us eventually this black point up here. So this is the final result in the large N limit. And you see that there is quite a sophisticated error budget here because, well, we have to control all sorts of systematic effects here. So the first systematic effect that we need to control concerns the higher order correction terms in the effective string theory. Okay, so whether it's a 1 over order 6 term, 1 over r to the 6th term, or a 1 over r to the 7th term. Since we don't know, we just have to look at the individual cases. We have to look at the fit range that we are using basically. So that's this part here. We have to take the continuum limit and we have to take the large N limit. Okay, and all of these errors here are really taken into account. Okay, so this was the extraction from the ground state basically. So I looked at the static potential. So are the excited states of the flux tube? Yes. It's a higher derivative operator. Now, don't ask me about the correct phrasing in the string on the string theory side. I'm unfortunately not an expert there. I think it's the TT operator. Is that correct? It's a TT deformation operator. Okay. I'm sorry. Yeah, I think so. But yeah, as I said, it's a boundary term definitely. But then I think it's a TT deformation on the boundary, as far as I know. But Michele, can you say more on this? Yeah, it's a boundary term, but yeah, I thought there was a different name to this in string theory. No, it's not a bulk. So bulk are actually all the terms with an odd power of R, and all the even powers of R are boundary terms actually. Yeah. Okay. All right. Yeah. I hope this helps. So, all right. So this extraction here was basically, as I said, from the ground state, so from the static potential. And now the question is, are excited states in agreement with that? And so what I did a test in 3-dimensional SU2 gauge theory. So extracting the excitation spectrum is actually way more difficult than just the ground state. So what I did was, for several lattice spacings, actually 3 different lattice spacings here, I just extracted the first and the second excited state with high accuracy. And then you can see that, so this yellow curve here is the result from this effective string theory, including this 1 over r to the 4 term. And you can see that in the large R limit, all these results nicely approach this curve here, the yellow curve.
and they actually approach it way faster than the pure light cone spectrum or whatever. So that is really showing that the results that I get are in nice agreement with that. There seems to be a slight overshooting here, but the problem is that really controlling all of these systematics in this region becomes more complicated. So I think this is really just possibly some residual systematics here that still needs to be taken into account. One can also look at the second excited state. Actually, in the light cone spectrum, there would be two degenerate states, and now the degeneracy is lifted by these additional terms. And it might be a bit hard to see, but one can really see this lifting of the degeneracy by looking at the open and the closed symbols. And also the closed symbols approach these solid lines here, and the open symbols, these dashed lines here, and also this is really visible if one can extract the spectrum at this accuracy. And one really needs like sub-per mil accuracy, okay? So this is really a tough task doing this accurately. Okay, so far so good. So this was all in 3 dimensions. So can we do the same thing in 4 dimensions, right? But the problem is really that in 4D, everything obviously becomes more expensive. So first of all, we have an additional dimension, but also the error reduction algorithms don't work as well. So this is a bit unfortunate. So one really has to invest more and more to get the spectrum in 4 dimensions, and I'm currently working on this. But currently, it's fair to say that there's not sufficient accuracy for an unambiguous extraction of this boundary condition, boundary coefficient in 4D, sorry. There are some first signs that it should be non-zero, but really pinning down the value of it, that is very hard. Okay, however, what has been done so far in 4 dimensions is to obtain a large number of excited states. This has been done both for closed strings by Andreas and collaborators, and also for open strings. And I'm just showing a few results for open strings from this very recent study here, where they could actually go up to light cone spectrum values for this n here up to 14. So this is really remarkable. I mean, this has not been possible previously. The problem is that individually for these results, the accuracy is not sufficient to extract the boundary coefficient or anything like that, right? It's remarkable that you can get all these, but extracting these subleading properties is currently just not possible. However, what has been found is some energy levels that are in agreement with having massive modes on the worldsheet. Okay, so this has been first noticed by Sergei Dubovsky, Rafael Flauger, and Viktor Gorbenko. Well, Andreas also had some comments in their paper already, but they could actually pin this down that there should actually be a massive mode on the worldsheet, and they called this the worldsheet axion. And the same state also shows up here as this yellow state. Okay, that's a very nice and interesting result. However, what is happening to these worldsheet axion in 3 dimensions? Okay, in 3 dimensions, there's no such state. So the question is why? So if you just look at the associated Lagrange density for this particular worldsheet axion, you see that there is this coupling term here, which couples the worldsheet axion basically to the string degrees of freedom. And this term is just not there in 3 dimensions. Okay, it just doesn't exist. So if we have this worldsheet axion in 3 dimensions, then it's basically like a free particle on the worldsheet. Okay, it will still couple to the string degrees of freedom by having this derivative here in terms of the worldsheet metric, the induced metric on the worldsheet, but this term here will not be there. Okay, so it basically contributes like a free scalar particle on the worldsheet, and actually this contribution is reminiscent of the contribution of a possible rigidity term. Okay, so the ground state contribution of this rigidity term can be written down. This has been done by Michele and collaborators, and also by people at earlier stages, of course. And yeah, the contribution basically looks like this. So where one now has another non-universal parameter, namely this mass m here. Okay, so what is happening with this m in 3 dimensions? So we can do the same analysis again, now including this massive mode and this contribution of the massive mode. Then, of course, we have one more parameter, so we get larger error bars. That's just what will happen, right? We need to constrain more parameters, but we can still do this. And actually what we see is that B2 gets a bit smaller. That's also due to the fact that there is actually a 1 over R term coming from this massive mode contribution now. So that's to some extent expected. But we can also extract this mass here and clearly get a non-zero result for the mass. Okay, so we can again do the continuum extrapolation. The results are shown here, and now we want to do a large n extrapolation for B2. That's now very tough, so I'm not showing any result. It will anyhow have a huge error bar, But for the mass, this is possible, and the result is this black point down here, and we get a value again with all the error budget, which is minus 1.34 in these units. Okay, so here now controlling the higher order corrections is much harder because you anyhow have one more parameter. So I was not able to do that sufficiently, so I don't give an error for that. But the rest of the error budget is still there. I think that's a typo. Take it as a typo. I have noticed it earlier, but I think it should be positive. Yes, actually, I know it should be positive because now I'm expressing it in units of the string tension. Now it's positive. Yes, sorry for the typo. Okay, so yeah, right. So I wanted to ask what I learned from this, so that's what I just wanted to say. I would like to express this in units of the string tension because Andreas and Mike Tepper have done have basically extracted the mass in 4 dimensions of the worldsheet axion in the large n limit. And so this is the value that I get in 3 dimensions. It has a rather large error here. And this is the value that Andreas and Mike Tepper got. So there is a slight difference here, but if you take this value at face, the difference is not so huge. One also has to say that this is not continuum extrapolated, while this is continuum extrapolated, and the continuum extrapolation actually brings the mass down. Okay, so it's quite conceivable that the mass at least is similar in 3 dimensions, in 4 dimensions, and that we are really looking at a similar state here. Okay. All right, so that was basically everything that I wanted to talk about today. I just let my perspective stand here. I'm very interested in any discussion on these matters, and I'm looking forward to your questions. Yes.
Out of time, but I think a state like that were there, Andreas and Mike would see in this excited state. In 3D, when I looked at the whole flux, all the citations that that by the
I mean, so why it shows up in this excited state, right, is because if you have this coupling term, right, it basically changes the quantum numbers, and then it corresponds to an excited state of being there, right? So you have a scalar particle, but it couples with this topological term, which gives it just a contribution with a different quantum number. Okay. No, of course, you have some higher order couplings, but higher order couplings generically would mean that they come with 1 over R to something contributions, right?
And there's a look at the range of R for string. Have you seen an excited state for this whole thing?
So for the excited states, the problem is that I don't know what the contribution exactly looks like. If someone can compute this, I can directly try to compare it for this. It is true that you don't see a massive mode contribution like this, that you see an energy splitting which has a massive mode in it. Exactly. But as I said, so if already the ground state gets a contribution by this, then of course it will not show up in just in the splittings, right? Not necessarily.
You mentioned quadratic approach there. Of course, there is this extra dimension, right? And people always thought that maybe there is a kind of popping of the string ball. But so far there was no evidence. Do you think it may have something to do with this? Basically, massive mode with string oscillating into this Quark event.
I don't know, as I said. So I'm not really from this part of the field. So it's hard for me to say anything about this. But okay, yeah, I don't know. It could be. Just don't have any.
Found that in the excited state, you would not quantum numbers, you would know if it's like very even.
The massive mode, you mean now? Yeah, so I think it's just a scalar. So it's then it's really parity even. No, of course not. But I mean,
it's like a linear dilator. Then it exists on consider.
Then
even for long things. You could imagine that there's a massive particle that leaves on the boundary. That's only there for both things. But this is not a boundary. So this having energy from the boundary.
Yeah, because when the
From a practical point of view, how long do you think, I mean, it would take, I mean, to increase statistics, I mean, to, let's say, verifying whether it's accurate or the accuracy?
You mean in my case, like to pin down the or bring down the error bar? It's tough. I mean, I think so. If you want to go to the large n limit, right, you also need to go larger n. And then you need to do a continuum limit for all of those. Of course, one could go like for one lattice spacing, say, and try to do it there. That would be easier. But already now it's not well, a cheap study, let's say it like this. So it evolved over time, got more expensive. No, not necessarily. I mean, it's just, I just wanted to know whether there is a massive mode or not, right? And that was my first goal. And then I found that actually I find a mass which is similar to the one in 4D. But of course, I mean, 3D and 4D is just not the same theory. So of course you can say if there is a non-universal parameter, why should it assume the same value? And I'm not saying that it has to, I'm just finding it that the mass is similar. If I extract the mass like this, and yeah.
The ground state, so you extract this mass, taking out that energy from mass, but one can also say that the universal one of after 7 pairs. So can you distinguish whether the data prefers standard form?
So if I include this, actually, I get agreement to way smaller values of R than if I leave it out and try just to fit with an additional 1 over R to 7. So in that sense, the data shows better agreement with it. But yeah, I mean, it's a tough task, right? I mean, you just have to, you can just compare like for different values of R, like how long can I describe my data when I go to smaller and smaller R's? And this is what makes it so hard to make any definite statement, whether this is now a contribution like this, or whether it's in 1 over R to 7 term. It could also be a mixture of 1 over R to 6, R to 7 terms, and higher order terms that just mimic this, right? I mean, you never know. You can try to do what you can, and then you can make statements. And
case strings, where one expects to find bound state,
one
sees them very clearly in the spectrum. Cited state. So there's no conspiracy there that it doesn't show in the spectrum state.
Okay, I think to thank Bastian again.
Thanks. I mean, all fair statements. How should you know? Yeah, but actually, I'm not so sure. I mean, if you have a massive mode of this type, right, and you do everything, then it shows up already. I mean, the thing is that if you have this massive mode only in the excited state with given quantum numbers, right, then you can clearly see it in level splittings. But if you have it in all of the quantum numbers, then how should you tell?
It's a great